So now let's continue with example number 2, design example 2. This one is the key protected door lock in the in airport or hospital. Keypad protected doors that require a person to press a sequence of button, i.e. a code. So this is just like the door with password. To unlock the door are needed. Consider a door may have 3 buttons colored red, green, and blue, and a fourth button to for starting the code, right? By pressing the start button followed by the sequence red, blue, green, and red again, unlock the door. So you need to press this start first, and then need to follow this sequence to unlock the door. Any other sequence would not unlock the door. And we have an extra output A from the buttons. Component is 1 when any button is pressed. Means that we have extras other than the red, blue, green signal. We also have extra signal named A when the button is pressed. Means that if we press uh, red button, for example, all right, so red signal will be generated, and another one is A signal. So have 2 signal, will be generated. One is the red and another one is A. Also, when we press the blue button, the blue signal will be generated, and also the A signal, right? A is 1 for exactly 1 clock cycle, no matter how long the button is pressed. So A is only 1 for 1 clock cycle. Means that if you press the button, something like this. So you have okay. So you have red button, for example. So when you press, and when you press, no matter how long you press here, so when you press for red button, for example, when you press, so the signal for red button will go from 0 to logic 1, and when you release, it go down to 0 again. And for example, this is we have the clock signal here, and let's say this is a positive edge. So and this is a signal. So when you press the button, red button, this A signal will go up to 1 for 1 clock cycle, no matter how long you press this. For example, if you have A, you press for very long like this also, it will 1 for 1 clock signal only, 1 clock cycle only, right? But it will be generated when you press any button. For example, red button, blue button, so it will generate signal A like this. And this is the state diagram for that. So your controller, your code detector is a box like this, where you have red for the input, green for the input from the button, blue button, and the start also. You have the start, and also the A. A is generated when you press any of the button, remember? All right. And U is the output of this code detector. When U equal to 1 means that open the door. When U equal to 0 means that the door is not open, right? So inside here, the behavior is this. And we need to generate the circuit for this, right? So before we can generate the circuit, of course, we need to derive this state diagram, which represent the behavior of this, right? So let's look at this when we reset, when we start our system. So we will in the state called wait, the wait state means that we wait for one signal, only one signal, which is the start signal. All right. So when there is no start signal, we will always in this state wait. You see, if s, this is s signal, if s equal to 0 means that there is no start button, start button is not pressed, so we will always in this wait state until s equal to 1. And when we in the wait state, the other signal are don't care, we only look at one signal s. So that's why we don't have any other input for this state. So if s equal to 1, we go to the next state called a start state. All right. So this start state will look at one signal, which is the red button. All right. Remember the sequence is red, blue, green, and red again. So when we are in start state, and of course in the start state or wait state, the door will not open yet. So u equal to 0. So in here, we only look at one signal, which is the red signal, which is R. And if R equal to 1, we go to the next state called red number 1. And only two signals that will force you to go from this start to this red 1 state, which is when R equal to 1 means that you press red button, right? And of course, when you press red button, A also activated. So A equal to 1, R equal to 1. Then you go to the next state. But if A equal to 0 means that there is no press. When no press, no any other button is pressed, means that you wait for the button to be pressed. But if you press, means that A is activated, right? But you press other than R, means that not R. Maybe you press green, maybe you press blue. So means that R should be equal to 0 in this case, or R not. If you press A equal to 1 means that you press something, but it is not red. So R not. So you need to go back to wait state. Means that the sequence is wrong already because you press other than red button. Right? Sequence is wrong. You go back. But if you press the correct one, which is R equal to 1, but others, of course, we don't care. We go to this state, red 1, called red 1. And at red 1, we look at the next button to be pressed, which is the blue button. Other than that, we will go back. Or if there is no press, we will wait here. So A bar means there is no press yet. But if A equal to 1 means that you press already, but whether you press the correct one or not. If you press the correct one, which is B equal to 1, so AB, so we go to the next state. But if you press other than blue, means that B bar, you need to go back to the wait state. Means that the sequence is wrong already. But if correct, blue equal to 1, so you go to the blue state. Again, at the blue, we will wait for one button to be pressed, which is the green one. So A equal to 1, G equal to 1, then we can go to the green state. But if no pressed, we wait here. If other than green, we go back. If correct, we go to green. And if green, we wait for the red to be pressed again. So AR again, go to red. And here, when correct, U equal to 1 already. Open the door and go back to wait. All right. But when we are at green, other than red button press, we go back to wait. All right. So this will represent uh, or will create this application. All right. But this is only the state diagram. So you need to derive your what? Your Verilog code. All right. So to derive the Verilog code, you need to have the structure of your finite state machine. And again, if I ask you what type of this state machine, is it more? Is it milli? So this is milli or more? Yeah, answer in less than 5 seconds. Come on.
I think it's more.
Yeah, this is more because
Sebab banyak masuk, dia boleh banyak keluar.
no. What is the difference between the more and the milli in term of state diagram? Tengok output dia tu. Look at the output. Here you see the output. U is the output, right? The output is inside the state. So this is more. Okay, let's go back. The output here, Z, inside the state. This is more. Here the output is outside the state, in the transition of the state. This is milli. Here the output is in the state, not in the transition. So this is more. Right? So this is more type. So we need to have the general structure. So now we need to have the flip-flops. This is our flip-flops. Let's say this is positive H. This is Q, D input and Q output. And of course, we have the output logic. And we have the next state logic. You see, it's the structure is the same, right? And we have this. We have this. You can name this as small y, or what we call the present state signal. And you can name this as capital Y, or we call it next state signal. And this is next state logic. And this should be the output logic. And we also have the feedback from this wire to here. All right. And the output, we have only U, the output. And the input, we have many. We have start. We have start is named S in this case, S. We have R, red, we have green, we have blue, and we also have A signal. Do we have any connection from here to and here to the output logic? No, because this is more type. More type, we don't need that. But if mealy type, we of course we need that. All right, that is the difference. So now, how many bit is this? How many flip-flop we need to use? So to know that, we need to look at our state diagram here. So we have how many states? We have 1, 2, 3, 4, 5, 6 states. So if you have 6 states, how many flip-flop you need to represent all the states? Okay, answer in less than 3 seconds. 1, 2,
3 maybe,
huh?
or 2.
How many?
6. 2. 2 flip-flop.
2 flip-flops. Okay,
Yes.
Izul says 2. Any other answer?
5 maybe Doctor. 5.
Huh?
5.
5. Okay, 5. Ada lagi?
6.
Huh? Jun?
6. 6.
Louder, louder.
6.
6. Okay, we have
Yeah.
Izun, how many from you? 5?
Izu says
2.
2.
Oh, Izun 2. Uh, Hasif,
Zizan Doctor.
5. Is it?
Zizan,
Jun?
yeah. I said 5.
6.
5, 5, 5.
No, yeah, yours one is 5.
Oh,
June 6. Okay, we have 2, 5, 6. Any other? Come on, there are many number. Okay, if you have 2 flip-flops or 2 bit, you can represent up to 2 power of 2, which is 4 state. So 2 is wrong, cannot be used because we have how many state now? We have 6 state. So if you use 2 flip-flops, yeah, 2 power of 2, you can only represent up to 4 states only. So cannot. 5.
So
2 power of
3.
5. So you have 32 state. So you can use 5, but it is wasteful because if you use 5, you have 36. You can represent up to 36 flip-flop. States. 32 states, and the circuit is big because you have 5 flip-flops, right? And if you have 6, 2 power of 6, which is 64, this is, wow, very big. You can use, but wasteful. So the best one should be
3.
yes, should be 3 because
3.
2 power of 3 you have 8. So if you have 3 flip-flops, you can represent up to 8 states. All right, so 6 is less than 8, so should be okay because you cannot use 2. All right, so 3 is the best for this application. So that is how we determine the size of our finite state machine. So this should be 3 bit. 3 bit means that 3 flip-flops, and of course this one is 3 bit. Get the idea?
Yes, Doctor.
Okay.
Yes,
So
Doctor.
now I don't have this Verilog code for this. So go back, try to derive the code on your own, and maybe you can share the answer with me. Or like Aman said uh, before this, right? That you need to do, and you need to submit this as you need to submit as maybe tutorial or assignment. Yeah. So I will maybe I will create the sub the submission link in author, so you can submit your answer, and let's see whether your answer is correct or not. But this is not compulsory. Yeah, I have another one for you. But if any one of you can or submit with the correct answer, all right, in the end I might give you a bonus mark. Yeah, who knows? Can you need marks at the end of the semester? So this maybe will help, right? So yeah, let's continue here. Next is what is called the ASM, or algorithmic state machine. So algorithmic state machine is actually the same thing from what we have learned before, except that the way we represent the state is different, where we will represent the state with in the form of flowchart instead of a state diagram like this. So for example, the state box, the box the state is now represented as box like this, as a box like this for more type, and the condition is represented like this, just like a flowchart, where we have here, from here we have the condition, and if condition is false, we go this way, and if the condition is true, we go this way. And we have the conditional output box also. This is for melee type. So the shape is like this. And to see how we use this ASM chart, so let's look back to the same example, and the first example where we have the automatic speed regulated car, right? And let's have the okay, let's okay, I need this this so okay, so this is the state diagram of the more type, right? So at state A, we look at W. So if W equal to 0, we stay at A. If W equal to 1, we go to B. So this is the ASM chart for this, right? Now from instead of drawing the state diagram like this, we now use the flow chart like this. So this is the state A, and we have decision here, and decision is from the input, right? So when W equal to 1, we go to state B. When W equal to 0, we go back to state A. All right. And we can write here, actually inside here, Z should be equal to 0, or don't write anything because there is no output yet, right? And in state B, if W equal to 1, we go to state C. If W equal to 0, we go back to state A, exactly like this. And in state C, here, Z equal to 1, so we have Z. Z here means that Z equal to 1. Here we don't have, means that Z equal to 0. Or you can write Z bar, or you can write Z equal to 0, and here Z equal to 1, same thing. If W equal to 1, we go back and still stay at C, like this. If W equal to 1, we are in state C. Still 1 again, go to state C. But if W equal to 0, we go back to state A, right? So this ASM chart is actually a very useful when the state diagram is very complicated. It's big, more than 3. Then the best way to represent the algorithm, the state machine, is by using the ASM chart rather than the state diagram. Now look at the milli. Okay, for the milli, so we have state A here, and remember, for milli, the output is at the transition. So state A here, if W equal to 1, we go to B, but if W equal to 0, we go back to A, and there is no output here. And in B, when W equal to 1, Z equal to 1, here at the transition. Z equal to 1, and we stay at B. But if W equal to 0, we go back to A. So this is how we represent a milli-state machine in arithmetic, algorithmic state machine. Yes, Sam. All right. Now, example number 3 is this. A computer system usually contains a number of registers that hold data during various operations. So inside a computer, we have many registers, to hold data or to store data. So sometimes it is necessary to swap the content of 2 registers. Typically, this is done by using a temporary location, which is usually a 3rd register. So in the computer, normally we have a register inside the microprocessor, for example. So we will have a register. So the register we have learned in this chapter, in the first subtopic of this chapter. So it is the same register, and the use of the register is to hold the data. All right. So for example, this one is called R1, register 1, and we have another one called R2. So for example, if you want to swap the data between these 2 registers, for example, this register is 8-bit in size. All right. So let's say the content of the register here is, I will write in hexadecimal number. For example, this is AB, 8-bit, A hexadecimal is in binary is 1010. B in binary is 1011. right? So I write in a hexadecimal number the content of the register. And for example, here we have CD. This is hexadecimal number also. Yeah, 8-bit. So this is 8-bit data. So what if we want to swap the content such that in the end we have CD here and we have AB here? If we have only two registers, which is actually impossible, because what? For example, let's go back to the initial content of this, because in the hardware, when you want to what we call the move to move the data from here to here, what you need to do is you need to put this into the wire, right? The output of the register, we call a bus in this case, right? And then we load that data into this, such that we have AB here. But the problem now is that when you load the data here, these R2 with the data from R1, the problem is that the previous data, which is CD, will lost forever. All right, because the data here, when you load into R2, yeah, from R1, when you load into R2, it will replace the previous data, which is CD, and this is lost forever. All right, so this one, we don't want to do that. We don't want to have that problem. So what we will do is that we need another register called R3, for example, right? Such that we can save the content of CD first in R3, so that we move or we copy the data here, CD, to R3, and this is saved here. Then we copy from here to here, such that we have AB here. Then we copy from R3 to R1, we have CD. Now we can swap the data by using this temporary register. Okay, so that is how we the things work in the computer actually. Now the problem is that how to get the control circuit or control unit to do that job. So let's say, for example, we have a signal that enable read. Yeah? We call it, this one is R1 out. This is read, means that we get the data CD here, or AB in at first, AB, CD, right? To get the data from here, so this signal must be activated, and to load the data, we call it R1 in. All right, this two signal is used to control whether the data can go out from this register or not, and this data can go in this register or not. Same as this one, we have R2 out, R2 in. This one we have R2 out, we have R2, sorry, this is not R2, R3, right? So in order to have the sequence of data movement, just like what I explained just now, we need to have the circuit, we call it the control circuit, that will activate this signal at the correct time. All right, and this signal, this control circuit, can be designed using finite state machine, FSM. Okay, so let's look at this. This is the structure of what we want to do. We have R1, R2, R3. This is the control circuit to generate R1 out, R1 in, R2 out, R2 in, R3 out, R3 in, right? Such that we can interconnection network is the bus, is the bus where the data can go out and go in, right? And the control signal, control circuit is this, and we have the input to the control circuit. The name is W to initiate the transfer. Means that if W equal to 1, we start the transfer. And we have clock, we have done signal, means that if done, if the process is finished, is done, this done signal is activated, right? So this is how we create the state diagram for that. So first, we want to save, remember, here, okay, so we have A, B, C, D. First thing is we want to save the content of R2 into R3. Here, we want to get CD here from R2 and put in R3 so that we have CD here. So what we need to do is we need to read from R2, means that R2 out must be equal to 1, right, to read the data from R2, and to write the data to R3, R3 in must be equal to 1. So in this case, R2 out is equal to 1, R3 in should be equal to 1 to do this operation. And to the next one is to copy R1 to R2 so that we have AB here. So now we copy R1 to R2, means that we read from R1, means that R1 must be equal to R1 out must be equal to 1, and R2 in should be equal to 1, so that we can read from here and write to here. And the last one is to have read from R3 to R1 so that we have C, D here. So R3 to R1, R3 out must be equal to 1, R1 in must be equal to 1, and again when the operation is finished, so done signal must be equal to 1 and done, right? So this is the state diagram, and this is the ASM chart that directly translated from here. So same thing here. So this is the wait, no transfer yet. If W equal to 1 means that we start the transfer. If W equal to 0, we stay at state A, same as this here. When W equal to 0, we stay at A. When W equal to 1, we go to state B. And when we state B, we do this R2 out equal to 1, R3 in equal to 1 exactly. And after that, here W equal to 0 or W equal to 1 is don't care. Yeah? Both will force you to go to state C, because you need to, once you start the operation, you need to finish the operation. After that, you go back, right? And this is the state table. So I want you to go back and try to understand this. This is the state table. And this is the state assigned table. This is the circuit, and done. Finished for this chapter. All right, this is for your homework also. Go back and try to understand this. And if you don't understand, you can ask me anytime, right? And we can discuss. Okay, so any question? Right, so with this, we are now officially finished chapter 4, and to help you understand better this chapter, I will give you one assignment, and this is a group assignment. I will create the group in order, and you can join the group, and you can choose which group you want to join, right? It's up to you to choose. Okay, any question before I explain the assignment?
No, doctor.
Okay, so if no, we look at the assignment. So this is the assignment, group assignment number 1. And remember, you will have at least 2 more assignment, group assignment. So this is 1, group assignment number 1. You will have group assignment number 2 and group assignment number 3. Again, this is for you to understand this chapter, this subject and this course better, right? Another assignment is for chapter 5, and the last assignment will be for chapter 6. So this is chapter 4. Actually, yes, Amal, you can finish this by midnight today. This is not that difficult. What you need to do is you need to design a vending machine. So the vending machine is the automated machine that provide items such as snacks and beverages, right, for you, where you need to put the coin in the machine for a certain amount, and it will dispense the item that you want, right? So this is the example. I give you one example where this vending machine is to dispense the candy, right? Where the price for the candy is 30 cents. Okay, so means that if the price is 30 cents, so you can insert 10 cent coin, 10 cent and 20 cent, and you get the candy. Or you can have 3 10 cents, one 10 cents, 10 cents, and another 10 cents, and you get the candy. Or you may have 20 cent plus 20 cent, and then you get the balance 20 cent, 10 cent back, right? So this is the example of the state machine, state diagram for that vending machine. And of course, I forgot the reset here. You should have reset. So for example, this state is called 10 cent, 0 cent state, where you don't insert anything yet. All right, when you have 10 cent, when you insert 10 cent, so it will go to 10 cent state. When you put another 10 cent, it will go to 20 cent state. All right, because 10 plus 10, you have 20, and you put another 10 cent, you have 30 cent, and f equal to 1 means that you get the candy. All right, it will dispense the candy. All right, G is the balance. Balance means that no balance. If G equal to 0, no balance, and go back to state 0 cent. All right, means that the process is finished here. But if here you put 20 cents, you will go to this state, 20 cents. And if you have another 10 cents, you will go to 30 cents and go back. Or you put 10 cents first, and another one you put 20 cents. You also go to 30 cents and you go back. But if, for example, you have this state, right, and you put 20 cents because you don't have 10 cents, so it will go to here, where even dispense the candy also, but it will return the balance, 10 cent balance for you, and go back to 0 cent. Right? So this is the example for 30 cent 30 cent candy. But in your assignment, right? In your assignment, you are required to propose and design a vending machine controller for item that the price is more than 30 cents. All right, not candy anymore, or maybe the candy is more expensive, 40 cents, 50 cents, or maybe chocolate, right? Or maybe other item that is more than 30 cents. All right, so you need to propose your own item for the vending machine, right? And you need to design your finite state machine, and of course you need to provide in your report, you need to provide the finite state machine, or maybe you want to use ASM, arithmetic algorithmic state machine, and you need to have your Verilog program, and also the structure, of your finite state machine. I forgot here. I will add the structure, the block diagram of your finite state machine, and the test bench, and also the simulation result. And you need to discuss what you have here, the result. And also you need to explain your the workflow, right, in your report. So I will give you 1 week for this, start from tomorrow. So here we are at 25th. So I give you until 2nd of June for this assignment. So actually this is not that difficult if you know how to derive the state diagram. And of course, after you have the state diagram, to derive the Verilog code is very easy, very straightforward. And remember, the structure of the finite state machine is always like this. For milli you have the wire. For more, always like this. General form of an AFM, right? It will always like this. So it should be no problem. So what you need to do is that you need to, the most difficult part is to derive the state diagram, to get the state diagram. Once you have the state diagram, you should know already how many flip-flop you need to use, right? And from that, you can generate the Verilog code already, which is very straightforward. Okay, so that will be your assignment. So I will post on Water so that you can have you can do your assignment. Okay, so that will be the lecture for today.